So hello everyone, thank you very much for coming to the seminars. So our speaker today is Nguyen Thao from Delft Center of System Control, Delft University. So he is a young rising star of our variance analysis community. And he's also moving around from Vietnam, Australia, Germany, and now Netherlands. And I guess Australia is his best favorite. That's why he joined us today to give a talk. So, and I guess you haven't been to Perth before, so welcome to Perth virtually. Okay, I think, so please join me to welcome him to his talk. So now it's on your space.
Thank you, Hoa, for your very nice introduction. Hello, everyone. First of all, I would like to thank the organizers for organizing this online seminar. Today, I would like to talk about projection methods for phase retrieval with high numerical aperture. This is the theoretical analysis and generalization of a solution algorithm my colleagues at TU Delft and I developed for an optical manufacturers 2 years ago. And this is the outline of my talk. After the introduction, I will explain the physics involved in this work. And the last 4 sections are a standard procedure of solving an applied problem. They are problem formulation, solution algorithms, convergence analysis, and numerical results. Let's start with the introduction. In this diagram, I explain in perspective the typical setting of the phase retrieval problem. Consider an imaging system, and this is the exit pupil plane. And the light is represented as a complex field and operating in the Z direction. An image detector is placed around the focal plane to capture the light. However, the image can only capture the intensity information of light, and the phase information is missing. So the phase retrieval is to restore the phase information of light. And because this is a very important problem in imaging, and the literature is huge. However, most of the studies are based on the scalar diffraction theory. And for that is only applicable to imaging systems with low numerical aperture. And for high numerical aperture, there have been only few solution approaches. And our task ordered by the company 2 years ago is to develop an efficient algorithm for their practical problem with high numerical aperture. Because a single image is not sufficient for phase retrieval, usually several images are required for this problem. And the relationship between the light in the pupil plane and the light in the focal plane, it determines the image formulation. And we will discuss this in the next section. So in this section, I try to explain the difference between the scalar and the vector diffraction theories. The scalar one is effective for imaging system with low numerical aperture. And the vector one is for those with high numerical aperture. We consider light as a transverse line wave cooperating in a direction k in a homogeneous medium with harmonic time dependence and satisfying the Helmholtz wave equation and all the Maxwell equations. Light is an electromagnetic radiation, but only the electric field carries the intensity of the light. So we only focus on analyzing the electric field as the solution to these differential equations. If we choose an orthonormal spaces n, epsilon 1 and epsilon 2 as in this figure, here n is in the direction of propagation of light. Then the two particular solution to the wave equation is in direction of epsilon 1 and 2. And the general solution for the electric field is a linear combination of these two independent solutions. So for the electric field at the point x at time t takes this form. It's a linear combination of the two particular solutions. And this term, the later term, e power minus j omega t is a time dependence term. It's non and can be dropped. And if the propagation direction is perpendicular to the reference plane, then this term is vanishes as well. Here the E1 and E2 as complex number. And if they have the same phase, and then the light is called linearly polarized. And because E1 and E2 have the same phase, so the electric fields reduce to this form. And here is the common phase. Phi is the common phase, and G is the amplitude of the field, and epsilon is the polarization vector. So we can see this is linear combination of the two fields. And this complex function is called a generalized field function. And the phase retrieval problem is to restore its function. So in this figure, this circle is the aperture of an imaging system, and F is the focal point. And the numerical aperture is the ratio between the aperture radius and the focal length. And after passing the lens, this is the polarization vector. This is changed by refraction. And for low numerical aperture, that is the radius is small relative to the focal length. Then the change of direction of this vector is small and can be ignorable. And this is the key simplifications leading to the scalar diffraction theory. And according to the scalar diffraction theory, so we have the light in the pupil plane and the light in the focal plane are related via the Fourier transform. But because image can capture only intensity information of the light, so we have the formula for the image at the focal plane like this one. Its intensity is the square of the amplitude of the electric field. So here F is the Fourier transform, and G is the generalized pupil function. But for high numerical aperture imaging systems, the bending of light after the lens had to be taken into account. That is, we need to know the relationship between the polarization vector before the lens and the polarization vector after the lens. And in this figure, we show the polarization direction before the lens in the direction of the x-axis. And by elementary geometry, the relationship between E and E prime is given by this formula. Here, this notation is the rotation operator around the OZ axis by an angle phi. And similarly, this is the rotation around the OY axis with angle theta. And the two angles, phi and theta, are uniquely determined by the incident point in the aperture. So it's clear that the bending of the polarization vectors depends on the incident point. in the aperture. So to calculate the bending of any polarization direction, so we need to calculate that for the two vectors, is x and is y. Is x in direction x, is y is in direction y. And for convenience, the aperture is normalized to have radius equal to the numerical aperture value. Then we can obtain the explicit form for the polarization vectors after the length for the two cases of polarization directions, like this formula. Here we have kx, ky, kz is the components of the unique line vector after the length. And kx, ky are the normalized coordinate of the aperture. Now let's show the imaging model according to the vector diffraction theory for the case of non-polarization direction. In this figure, we show the case of polarization direction in the x direction, is in the vertical direction. And we have the three components of the polarization vector after the length. We have three, can be considered as amplitude modulation of the generalized pupil function. And because the three components are incoherent, so we have the total intensity is the sum of the three intensity components, like this formula. Just as a technical remark, because the normalized coordinates of the generalized pupil function is on a unit sphere, but it is measured in the pupil plane. So in numerical calculation, this function should be normalized by an obliquity factor like this one. So for the case of unknown polarization direction of light, so the direction is considered as a random variable. And for this, the image is the average of the two positive functions for the polarization direction x and y. So we have the image formula. Here we have 6 components. So the first three is for, in this figure, the first 3 is for polarization direction in x, and the last 3 is for the 3 components of the positive function for the polarization direction y. So in the SQL, we use this set denotation for the sets of 6 components of a vector positive function. It's clear that the vector imaging model is more involved than the scalar one, and it's of course more expensive in terms of computational complexity. So it's very important to know when this model is really needed instead of the scalar one. So in this slide, I compare the 2 imaging models for different values of numerical aperture. Here's the cross section of the scalar and the vector imaging model is plot. And in the first row is for the case of no operation of the generalized pupil function. And the second row is for the case with operation. So we see the different shape of the imaging model. And the first column is for small numerical aperture, that is 0.15. So we see that almost no difference between the 2 imaging model. So in this case, we definitely not use this vector model. And here for numerical aperture 0.55, and one can observe small difference between the 2 imaging model. And in the last column, we have numerical aperture is 0.95, and this is the case of our primary interest. And we see that bigger difference between the two imaging model. And in this case, that's why we need the vector phase retrieval for high numerical aperture. So you can see from here. Now let's go to the problem formulation. Again, we use this figure. We consider phase retrieval given several images. Here we have m images. For each image, this is the vector imaging model we just discussed in the last section, and omega represents noise. And for each image out of focus, for example, this one, out of focus with distance ZD, so it should be compensated by a phase diversity term, is a phi D, and the relationship between phi D and ZD given by this formula. And this is a non, because S, Ky is the normalized coordinates of aperture of the generalized pure function. So given the images, m images, phase retrieval problem is to restore the phase where the amplitude can be either known or unknown. And this is clearly an feasibility problem. Actually, where we want to find a complex signal that satisfies all the data constraints and a variety information of the problem. So to formulate the feasibility problem model of phase retrieval, we need to describe all the constraints in the same ambient space. Because the vector imaging models has 6 components. So the ambient space is defined as a product of 6 components like this one. And now we describe all the constraints of this problem. First, the general constraint. So this set to capture all points with the components having the same phase, and have proportional amplitudes. And when we find a solution in this form, then X is correspond to the desired generalized pupil function. And second is the intensity constraint. This comes from the image. And each constraint consists of all possible points that can generate the image. And if the amplitude of the generalized pupil function is known, and then we can tighten the general constraint to the amplitude constraint. So here we have more information here. Only phase is unknown, the amplitude is known. And a decisive step to solve a feasibility problem is to calculate the projectors. So let's just compute the projectors and discuss the projection methods. For example, just yes. So there's several ways to formulate a feasibility model of the phase retrieval problem, but here it's more convenient to formulate the problem as a two-set feasibility problem. Here the set A is that's the m time copy of the general constraint set, and B is combines all the intensity constraint. And of course, if the amplitude of the generalized pure function is known, and then the general constraint is replaced by the amplitude constraint. So we are going to compute the projector and discuss projection algorithms. For example, we discussed the projection on the general constraint set omega 0. A point U in the ambient space. So there it has 6 components. For example, here they are different, have different phases and different amplitudes. And a projection of U on omega is the set of consisting of on points in omega that are nearest to U. And the general constraint set omega 0 contains on points that have with components having the same phase, for example here, and proportional amplitude, for example here, the green one and the blue one. And by calculation, we can have the explicit form for this projector. And similar, we can also obtain explicit forms for the projector on the intensity constraint and on the amplitude constraint. And from the projectors on omega 0 and omega d here and omega g, so we can compute the projector on the set A and B defined in the previous slide. So here's just a product of projection on the omega 0, and here's just product of the intensity constraint. So from now we can implement any projection method for this problem. And it's widely known that projection methods are the most efficient class of algorithms for scalar phase retrieval. And in this study, we extend them to the vector phase retrieval and do the analysis for the first time. Here we recall some projection methods, such as alternative projection. Let's see, we for 2 sets A and B, we do project on one set and projection on another set, and keep going. And we expect that the sequence will converge to a common point of the 2 sets. The Delft-Rayford algorithm or Phenop's hybrid input-output method, or the RA algorithm or the trap algorithm. For example, in the next session, we will discuss conversion of the alternating projection. This is the most simple algorithm. We will follow the analysis scheme based on the theory of almost average operators. There are 2 conditions for convergence. Because the problem is non-convex, the fixed point operator is not a contraction. So the first condition is the almost averageness. That means the next iteration is not too much farther away from the reference point compared to the current iteration. So for example, in this figure, so this is the reference point, and this is a current point, a current iteration, and here's the next iteration. So this condition ensures that the next iteration not move too far away from the reference point compared to the current iteration. And the second condition is that the problem is regular around the solution. This regularity condition compensates for the possible expansiveness of the mapping in the other mapping. And this condition also means that the step size, so this term x minus x plus, this is the step size. This condition means that the step size is not too small compared to the distance to the nearest solution. And this condition actually is a necessary condition for linear convergence of any fixed point iteration. So before apply to the alternative projection, let's discuss the geometry of this problem. In general, the geometry of the vector phase retrieval is equivalent to the geometry of the scalar phase retrieval. That is the on the constraints are prox regular sets. Recall that a set omega is prox regular at a point x bar if and only if the projector is single value around this point. And circles are typical examples of regularity. For example, we consider the general constraint omega 0. We check this in the formula for the projector on this set. And the U is a point to project on omega 0. It's U, CC is are the components of U. So this formula is the formula for the projection. It's the amplitude. It's uniquely determined by this one. And the phase in this form. So if the term inside the brackets is non-zero everywhere, then the phase is uniquely determined. That means that the projector is single value. That means we have regularity. And we can have and this assumption, this non-zero of this term is a natural assumption of the phase retrieval problem. And we have similar results for intensity constraints and amplitude constraint. So back to apply to the alternative projection. So the geometry of the problem, that means the prox regularity of the constraint sets give the almost average of the fixed point mapping. And the second condition about regularity property reduces to the subtransversality property of the collection of sets at the reference point. So in phase retrieval context, the subtransversality property is the negation of the tendency. If we look at this figure on the left figure, here we have subtransversality property. And in the right figure, we don't have this property. We have tendency. So for convergence analysis for other projection algorithms can also be obtained, but it's more involved than the alternating projection. And in summary of the convergence analysis, so we can extend the geometry and all the convergence results of scalar phase retrieval to the vector phase retrieval. We now show some numerical results. This is a simulation, but is closely relevant to a practical problem we solved 2 years ago. And this plot shows the advantage of the vector phase retrieval compared to the scalar one. And the results of 75 numerical experiments are summarized in this figure. Here we have 3 algorithms. Some AM we mean the alternative minimization, but here correspond to alternative projection for scalar phase retrieval, and the VAM is alternative projection for vector phase retrieval. And the one with the plus sign is indicate that the amplitude of the generalized pure function is none. And we observe that the difference between the two, between the scalar and the vector phase retrieval, is more for higher numerical aperture. So because our primary problem is for numerical aperture 0.95, so that's why we need to develop the vector phase retrieval, because it's get more and more error. The scalar phase retrieval gets more and more error for higher numerical aperture. So this is the noise analysis for the case for numerical aperture 0.95, and also the result for 75 numerical calculations. Here we observe that for the scalar phase retrieval with error about 10% is less sensitive to noise, because we have, and the vector phase retrieval is more sensitive to noise. But this is not a surprise, because if we compare the two imaging models, the vector imaging model is more involved, and then that's the reason why the vector phase retrieval is more sensitive to noise than the scalar one. And linear convergence of the alternating projection also consistently observed in the last. These two curves is for the case without noise. We only saw for the first 150 iteration, and if we go further, still we observe straight line in this direction. And here's for the case with noise, and then the algorithms also behave well, as expected. So it's a particular example of phase retrieval we calculate. In this figure is the data phase we use to generate the images, and we add noise. And here's the phase restored by scalar phase retrieval with error is like 15%, and this is really less accurate compared to the vector phase retrieval with smaller error without and with amplitude information. So let's just briefly compare the different projection methods. So if we calculate for many for the projection methods we mentioned in section 4, that alternating projection, Doppler effect, FinOps, hybrid input-output, and the RA and the drop algorithm. And we observe that the RA and the drop algorithms are most effective for this class of problem. For both cases, with amplitude constraint and without amplitude constraint. And the other algorithms are less effective, and we do not solve in this figure. And here we mentioned that the alternating projection is here. The one is alternating projection is essential for all cases, because it's useful for suppress noise and stabilize the final estimate. So here's in summary, we have extended the class of projection methods from scalar phase retrieval to vector phase retrieval, and we explain and analyze many theoretical aspects of this solution approach, and all the non-convergence results for scalar phase retrieval can be extended to the vector phase retrieval. And we formulate some numerical results. This is actually deliverable to our customer. And the drawback of the vector phase retrieval is that it's more sensitive to noise than the scalar one. And here's the first part, the main references. Part 1, and here's the part 2, and the main results of this my talk are being prepared in this manuscript, the same name projection method for high numerical aperture phase retrieval. And our project is supported by the MacInfo project. And we are a contributing team from TU Delft. Thank you very much for your attention.
Yeah, thank Thao for your very nice talk. So if anyone has questions, you can just raise your hand, just unmute your mic or type in the chat to our speaker. Any question and comments?
I can't find how to raise the hand. Sorry, can I just ask the question? May I?
Yes.
Okay, thank you. Thank you, Thao, for your presentation. For me, it was very interesting to see how a physical problem, which seemingly is very far from what we are all doing here, or at least for me, very far from what I am doing here, can be somehow reformulated in mathematical terms and can lead to something which we know, like feasibility problems, alternating projections, Douglas-Rashford, and also convergence analysis using our regularity concepts or transversality concepts. So for me, it was actually interesting surprise also to see how far and in which direction you moved after leaving Australia. My question, in fact, I have a couple, but my main question actually is concerns terminology. So you are using, of course, subtransversality as a condition ensuring linear convergence. On the other hand, on another slide, you talked about metric regularity. You are looking actually at this slide number 26 to simplify your life.
Yeah.
And there is some, okay, here, part B, subtransversality somehow leads to metric regularity. And I'm a bit surprised here. I would expect sub-regularity on the left.
Yeah. Yes, right, Alex, it's, yes, because you're definitely right. Just I use confused terminology, because in this paper we use the metric regularity in the sense of Yorfe, based on Yorfe paper in 2011, and it's a little bit it's like regularity with respect to a particular set, not at a reference point, like in the conventional definition. So so what we use metric regularity is a termination, but actually but actually if we reduce to a point, a reference point, so this should be metric sub-regularity.
Okay. In fact, there is a lot of confusion in the literature in terms of terminology, and maybe 10 years ago, there was a group of people who really insisted on calling sub-regularity regularity. I think now they have given up, but probably there are still some traces in the literature. Okay, thank you for clarifying this. One more terminological question. You mentioned somewhere Picard iteration, and I know that you and Russell often talk about Picard iterations, and I've been curious for many years already. What does Picard have to do with what you are using here? You have never explained why Picard, neither you nor Russell. So can you explain now why Picard?
Easy. It's a pity that Russell is not here.
So you want to refer the question to Russell?
Yeah, maybe Matthew, do you know this one? I don't have the answer to the question of Alex.
I think the answer is because of Charles Emile Picard, who developed fixed point iterations for approximating solutions of differential equations. So at least I think that's where the name comes from.
So there are some historical roots. It would be not bad probably to mention somewhere this connection, not just using some name, but what's the role of this guy in your analysis? Okay, one more question, if I can. In the very end of your presentation, you mentioned some industrial customer. Of course, it is clear that the whole this theory, it was not just for your fun. And what do they want actually from you, and how happy are they with your results?
And there's quite of the content is confidential, but they do.
I'm not asking to give names.
They are an optical manufacturer. They try to improve the accuracy of their imaging system product. So for that, they do want to do the correction of the imaging system. Which one? I do not know actually. And they just give out the problem. They say that this is the phase retrieval problem. But because this imaging system is with high numerical aperture, and the conventional phase retrieval algorithms cannot be applied to their problem. So they ordered our group at TU Delft. Unfortunately, we try many imaging models, but because they don't know what exactly the imaging model for their system, and we try several ones in the literature, and at the end we're successful with the imaging model we call the vector Poisson function, and we get the good model for their problem, and we develop an algorithm for them, and they're happy and then pay the money. Then they did not say anything more.
This last argument is the most convincing one. If they pay money, of course they're happy. Okay, thank you, Thao.
Thank you, Alex.
Thanks, Alex, for your questions. There are many other interesting questions in the chat. So we're going to start with, I'm sorry if I pronounce your name wrong. Alex, can you help me to say his name?
So the question is from Evgeny Nurminsky, and he asks about the relationship between transversality and tangency. TR in some subspace and 10 in the complement. Does 10 poison the convergence? Okay. Thao?
Sorry, Alex, I cannot hear well the question.
But can you read the chat?
On the chat, you can click on the chat.
Where I can read the chat?
At the bottom, you have participant chat and share screen. And
should I stop sharing my screen first?
No. Just click on chat and you will see the discussion.
Yeah, but I think because the video is recorded, so I will read the questions clearly again. So in your presentation, you mentioned transversality and tangency. And then it's quite about something about the mixed case when some subspace and tan in the complement. So does tan poison the convergence? So if
yes, because for the phase retrieval problem, when we formulate as a feasibility problem and the constraint sets, basically they are regular. So geometry they just like product of circles. So so in this case, so we image simple, in the simple case, we can imagine two circles, and we have subtransversal and tangency. Basically, they are just a negation of each other. So in the very bad scenario, we get they are tangent, and we get very slow. If convergence is very slow, but if they intersect, and then we got linear convergence. Because the set is basically rock regularity, basically almost convex. So locally, there must be linear convergence.
But the question is about the mixture of the two. If you have a little bit of regularity in some subspace, but in some other subspace, they're tangent.
No, the subtransversality is not depend on the ambient space.
Good.
It's a key difference compared to the stronger
transversality.
Yeah, but for subtransversality, we don't face this problem. Yep.
Okay. Thank you very much for your question and your answers. So we have another question from Gary. So can you read the question or to the?
If you use a product subspace formulation for projections onto multiple sets, you tend to get a very slow convergence because the diagonal set is very thin in the space of all end products. And the easiest way to think of this is if you've just got two convex sets and they intersect non-empty intersection, the classical Douglas-Ratchford algorithm applied to the two convex sets will converge in a finite number of iterations. But if you reformulate that as the two sets and a diagonal subset and sort of the product set formulation, because the diagonal set has empty interior, you get effectively, you have to do an infinite number of iterations to converge to the fixed point. So my question was, have you tried other formulations as opposed to the standard product set formulation to see if you can get faster convergence rates?
Thank you, Raghi. It's a very interesting question. I'm happy to answer, to address your question. We have many ways to formulate feasibility models of phase retrieval, because here basically we want to find the intersection of the general constraint set and on the intensity constraint set, and so we can formulate as a multiple set feasibility problem or two set feasibility problem, because if in the case of simulation or the case of very little noise, we can do the cyclic projection of the M sets feasibility problem. We get very fast conversion. But if in the case with low signal to noise ratio, that means we have more noise. And then we do cyclic projection. After 4 or 5 iterations, we get no improvement of the estimate. So the two set feasibility problems is advantageous in this sense, because it's in general we can do kind of average, and then it suppress noise. That gets an average, and then we got a good solution. Of course, when we do alternative projection, we got very slow convergence. Actually, we get infinite iteration. We get to nowhere because it's very slow. That's why we need to other projection method, like for example, we get Doppler-Rayford. It's get faster. It's in phase retrieval. It's due to FINOP, like 40 years ago. It's get faster conversion, but because it is very sensitive to noise and it cannot apply to problem with noise, and if we have more modifications of the Doppler-Rayford, we call relaxation version of the Doppler-Rayford algorithm. For example, we have like FINOP hybrid output, the rise and the drop, and we check them, and then these two algorithms seem to be the best for retrieval problem so far, because in this one actually for problem with 7 images, we need only like 10 iterations to get the final estimate. If we have like 5 or 7 images, we get like 10 iterations is sufficient for retrieval.
What values of beta do you use in the RA and the DRAP?
Here because if we do here is the Doppler-Redford algorithm, if with the noise, the two sets of the feasibility problem is inconsistent. That means the intersection is empty, and the Doppler-Redford operator has no fixed point. That means we got no convergence. But if we do some kind of relaxation, for example, with the RA algorithm, is introduced in 2005 by Russell Luke, and it's also kind of convex combination with one of the projector, and then we got very good result. And
if you have noise, don't you just simply expand the sets inflate the sets by the amount of noise you've got so that you will get an intersection? Or do you not, you just use the noisy values but assume that they're infinitely precise?
Yes, in the literature, there are two ways are used to address this problem. The first one is, as you said, we can, if the two sets do not intersect, we can enlarge them in such a way that the enlarged sets do intersect. And then we do solve the inconsistent feasibility problem. But in practice, this way is super expensive, and usually is require more information about the noise. And the second approach is we just use the noise data, and we solve the inconsistent feasibility problem. But in this sense, we find some kind of best approximation. We do not find the point in the intersection, just some kind of best approximation to the problem.
I just want to make one final comment about that then. If you use these relaxed operators, then I think you lose the key property of the Douglas-Ratchford algorithm, which that it can walk away from local minima that are not in fact intersections, proper intersection points. And I would have thought that if you know what the noise levels are and you can sort of inflate by that amount of noise, then you will not get trapped in local minima, which unfortunately the regularized algorithms might do to you, especially phase retrieval, because it's got, in the one-dimensional case anyway, it's got lots of local minima.
Yes, this is a helpful comment. But we try to, the case of, if we consider the case of phase retrieval with only 2 images, then we face the problem with local solutions. But if we try some phase retrieval with 7 or more images, so in this case, it seems that we do not face the problem of local solution. That's what we try to numerical simulation, and yeah, and then we focus. The main challenge is to get convergence or not convergence. We do not pay attention too much to the local or global solutions. Yeah, thank you very much for your comment. Very helpful.
Thank you. Thank you, you both, for very thoughtful comments and questions. So we have one comment from Vera to Gary. So Vera, you want to ask Gary about the reference?
I was just wondering, because embarrassingly, it's the first time I hear about this, that project formulation may not work. So I thought that maybe you have some clear reference on this, but yeah, it's also an important comment.
it's not so much fairer that it doesn't work, but it's just the convergence can be much slower than it should be.
Mm-hmm.
If you want a reference, I can't think of one off the top of my head, and I'd point you to a real expert on this, which is Matthew. I think he could probably give you one.
Who? Sorry.
Matthew Tam. He's on the.
Okay,
he's on the list.
I'm going to torture this guy.
Yeah. But yeah, he'll know more than I do.
Okay, thank you.
Thank you. I have this. So if no one have questions, I have very naive question to Thao. When you mentioned about the noise, so what do you mean by that? I'm not. Yeah.
Noise.
Yeah, I mean the convergence. The not mean the convergence numerical result.
Numerical result.
Yeah. Numerical. When you solve, when you show us the.
This here. Okay. Yeah. If we do the simulation without noise, then when we have accurate imaging model, and then we can observe that the convergence we go to correct solution for the experiment we do. But for experiment with noise, that means we have inconsistent feasibility problem, and then alternating projection we find this is the best approximation, and this is this error, and it gets stay here. Like best approximation, it cannot improve further.
Yeah, because of inconsistent case, and that the distance, right?
This because here we do simulation, so we can actually calculate the real distance from the current estimate to the correct solution.
I see. Yeah. So
with noise, we cannot get to that because it's inconsistent.
Yeah.
So this.
But what is converged is not of course it's not zero, but of course it's converged to it stop as the distance between two sets, right?
That's what we hope. But from calculation, we cannot guarantee. But that's what we hope. That's the distance between the two. Yeah. Because for 7 images, then 7 constraint sets, we find some point that doesn't belong to anyone. But in a sense, like for example, the sum of all the distance to each of the sets is smallest in a sense.
Yeah, are you considering product space, and then actually you just consider two sets, and then you have a norm, and you probably have the distance between two sets?
Yes, it's for two set feasibility problem. We have a lot of convenience in terms of interpret the result. But actually, we do algorithm on two set feasibility problem, but it's equivalent to the algorithm on the sets. It's just convenient to apply because most of the algorithm is designed for two sets feasibility problem. But that's the convenient. But actually, in nature is so for on the sets, not just two.
Yeah. Okay. Thank you very much for your answer.
Thank you for your question.
So, is there any questions from the audience? Okay, so please join me to thank our speaker today for his interesting talk. Thank you very much for your coming. And
thank you, everyone, and I wish you healthy and all the best.
Thank you, Thao.
Thank you.
Thank you, Thao.
Thank you.
Thank you.